gonna get started, Adam. I'll share my nmrbox screen. So, this is top spin. Let me. Okay, hold on. Where is it? My box. How do I go? Oh yeah, here. Okay. I have a top spin running, and I'll use it briefly for showing some of the data. Okay, so as I said, I have a list of examples for all the data sets. And from there, you get some idea what we're going to cover. But I'll walk through one by one, and until we're running out of time. Some of the reconstruction may take long. Even the 4D definitely takes a long time, so I suggest that you not to run them. Some of 3D could take a half hour as well, because almost all of them, are high resolution and very big matrix. So some quick one takes a few seconds and then to a few minutes. So I'll let you know when you can run. Okay. The other thing is that if you want to run it, you might want to rename the directory for the data so that if it gets overwritten, you can get that back quickly. So the first experiment we want to show is this constant time. So go to my data directory.
Jinfa, before you get into that, I just want to make one quick comment for everyone. All people that have registered for this workshop will have a copy of this data automatically put in their home folder. So you can see in Jinfa's terminal, he's in his home folder, then inside another folder called Summer Workshop 2020, and then in a directory with his username. You will all have that copy in your home folder to work with for this tutorial.
I was going to ask about that. I was on the wait list up until this morning. I don't see that folder in my home directory.
Okay, he can copy by himself, right, Adam?
Yeah, I can take care of that offline. I can put a copy into your home folder while Jinfa continues.
Yeah, you copy the first one first, and by the time everything else will be done. Copy this first, Adam, for him. Okay.
Okay.
So let's go to constant time. HSQC C13. It's a US, means uniformly sampled 2D. It's a two-dimensional. And this is an example that I presented in the second talk. If you look at it, it's a standard Bruker data set, although I didn't use the Bruker post sequence. It's just HSQC without C13 decoupling. And the first thing when you get the data, what you do is type Bruker, right? The command within NMR pipe. If you type that, you see the TCL interface Frank did. And if you say read, that will try to read it from ACQS and post sequence file and try to set it up, the conversion script. This is the graphics, and this is the script that you're gonna see. It will be saved. Now, one thing unfortunately is that our own sequence, Frank's things is really optimized for Bruker standard sequence. For our own, it doesn't really read some information correctly. For example, this thing, actually this might be right. Yeah, this is right. It's carbon frequency, and it's 1/2 IN0. It's a spectral width, and it is echo, anti-echo, and these are right actually. You can always save that, but don't save it because I already have it for you. Okay, just in case that it's a new data set. When you get a new data set, that's how you do it, and you generate this FID.com file. That's the conversion script that I already have it. A slight different from what Frank has, because the new script now try to scale the intensity because Bruker does things by scaling. Okay, so Frank tried to be consistent with that, and this older script doesn't have it. If you don't compare the data, you don't need a scaling. The scaling is really when you compare two different spectrum or the same, you know, two different protein or same protein to two different spectrum. And then you do scaling and then it should be the same. Okay, so this is a conversion script that we saved. Read the SO file and try to generate a pipe FID file. And if you run that, you can run that because it's quick. Oops, you need a /FID. So you generate this test.fid file, okay? And test.fid file, right? And you can open that to look at it. You can get a horizontal slice type etch, and you can do that. Look at it. You can do process, right click or pluck, auto process. You get a 1D slice like this, and that's a good way of checking whether you have baseline distortion or anything like that. All right, the data looks very clean. It was run on triple axis gradient probe. Didn't have, it was in H2O, and it didn't have the pre-saturation. It completely rely on gradient to kill water. So after this, I have a script called ft2, I believe. Yeah, ft2.com. So this is just a Fourier transform, process both in direct dimension and indirect dimension. And I don't know actually if Frank has any way to automate. Actually, they do. He does. Now has something called a basic ft2, which actually can generate something like this for you. But to be honest, I've been used to this old way of doing things, so I'm not very familiar with his new script. So I suggest that you look at his tutorial and other nmrbox workshop, and you'll probably learn and do better than me. So I always just copy paste different script and edit them. That's how I do it. So in this case, this is the first example, so I just want to go through this. For those of you who are expert, bear with me. I'll try to be quick, okay? So you read the data in, you apply the window function right here, then you do zero filling, followed by FT, and then phasing, okay? And then you extract a small range because I just want to show the upfield part, the method part. So it's really from 2.6 ppm to 0. And you transpose the data so that the indirect dimension becomes the current dimension. And you do the same thing as you did for the direct dimension, right? And then you transpose back and you still do a little bit baseline correction. Although the data looks already very good, but it doesn't hurt in the end to do it again, just in case there's a little bit of offset or something. And in the end, I write down as test 28 millisecond. This is a spectrum, meaning that's a 28 millisecond acquisition time, okay? So if you look at this, I have 28 millisecond and 56 millisecond from another experiment that I don't have the data, but just the spectrum, okay? And so if you do FT2, these are quick, so you could run it. And you can open up test 28 millisecond, you see the spectrum, okay? Now, let's look at this Smile script, smile.com. So as you can see, this is really the same as without this part, with this appetization function uncommented. It's really the same as ft2.com, okay? And, but we want to use Smile to extend the acquisition time by 100%. So it has 246 data point increments. So we set this XTCT because it's constant time. So we just set constant time. The other thing is that it's X dimension. So in direct dimension, for Smile, it's always the case that the direct dimension is put it as the last dimension. For 2D, the direct dimension becomes Y, and the first indirect dimension becomes X. So that's why we use X here. So here's a thing to answer the question that one of the attendee had, is that how do we optimize that? Well, the default of this is 0, okay? So therefore, you need to tell the program what's the constant time, points. It's 246 points, but we extended it to 486. Whether it's a constant time or not, it doesn't matter. You could do equal well by XCT of 246, 243, and then you do XT of 486. So the difference is this. This just tells the program that all the 246 data points is collected by constant time. Okay, so therefore there will be no decay and no line shift simulation is needed. But the XT tells the program that you want to extend the acquisition time to 486 points. So whether you have 246 or other data points, it's always extended to 486. If you don't specify this, by default, the extension is about 50%. So in this case, will be 246 times 1.5. Okay, that's by default. And that's a good default for NUS, but for fully sampled, and often we do 100%. So in that case, you have to specify. The default is not optimal, okay? The other thing is that the phase correction is always 0. And SMILE is actually assuming that the spectrum is in phase, absorptive. So you really, it's very critical that you really apply the right phase correction, okay? Now, some people may know, I don't know what is my phase correction. So what you could do is that you can run the version without SMILE and pick up the strong peaks and phase them, okay? Even for 3D, 4D NMR, and you can always do that. Expand them, zero fill, expand them, process them just as if it's fully sampled, and check the phase. And also you can check, like FT, usually you have a negation, right? Negate the imaginary so that you reverse the axis, or you do sign alternation, swap the bottom downfield part with upfield part. So all these things could be checked without SMILE before you run it, okay? So like in this case, we get it from the previous ft2.com, and we figured out that we need a phasing of 93.8 as a linear phase is 0, okay? For epidization, these are default. The default is a cosine. It's a sine wave. And then SQ1 tells the program how much is shifted. 0.5 means that shifted it by 90 degrees. It's whatever that point times 180. So 0.5 times 180, 90 degrees. So you become a cosine window. And then XQ2 tells me when the cosine window stop. Here it's 0.98. So roughly about 172 degrees. And this is a power. So corresponding to really regular NMR, SP, dash off, dash and dash POW, power, okay? So 2 means that you use a square of the function you have. So in this case, it's a cosine square ending at 172 degrees. And these are the default. You can delete them. You don't need them, okay? For example, oh, geez, sorry. You can just delete those. Now, by default, we use a cosine instead of cosine square, because usually we do 50% extension. We don't want to use a cosine square. Then the extension is too negligible. But when we do like extend this time domain data by a factor of 2, we often use the power of 2 using cosine square. So you could have just used this, and the script will work equally well, okay? And after that, it's already epidized by the window that I was talking about, by this window, okay? Therefore, you don't need a expedizer again. And also, this scaling factor, depending on the linear phase, is also automatically set by SMILE, and it's not undone, meaning that it's going to carry over to the later processing. So you really don't need the whole line over here. That's why I commented out. Okay. So I'm not going to save this, although it's equivalent, but so you could run Smile. Oh, another thing is that this report is that if you don't have this, Smile stays quiet, nothing printed out. You don't see anything. But report one is that you're going to get some information displayed while Smile is running. And default is 0. And 2 will give you more information. So this is just about how much information you want to see when Smile is running. Slash means that the default is 0.8. Okay, it's really for something fast, quick and dirty reconstruction. But we usually use a little bit slightly higher value for real reconstruction so that we slow down the convergence rate, and so to exchange the speed for a little bit better quality, hopefully. And if
can I ask a question?
Yeah.
Okay, so what's the default scaling parameter for a Smile?
Scaling.
You didn't
default
put it.
Scaling default is 0, meaning that.
No, first point scaling parameter.
Oh, first point scaling factor based on your linear phase. If it's 0 or plus minus 45, it's 0.5. It's 180 plus 9 minus 45, it's 1. And 360 is also 1. Okay?
Okay, thank you.
Yeah.
Can I ask a question?
Yes.
So I've been using nmrpipe to automatically generate scripts, and then I've been tweaking it manually.
Yes, the basic FT2 or something like that.
Yeah. I think so.
Yeah.
When I generate them, I get ndim2. Should I reduce that to 1?
Oh, ending never be 2. You mean the SQ2 here? Like this this value?
Sorry, it's the number of dimensions, I believe.
Oh, ndim. Oh, this one. Is that what you're talking about? No, it should be 2. It's the total dimension of the data set. Okay, and nowadays the new version just automatically figured out from the header, so you don't need this information. That's why I don't specify this. But some of the example file use the older version, and you need to enter it before the Smile could run. Okay, thanks for the question. Yes.
So one more question.
Yes.
Oh, okay.
Yes.
Yeah. Hi. My name is Siddhartha. And in your Smile, your data points, right?
For this application, yes.
Yeah. So I mean, I guess I should not be asking this question at this time till I see the results. So, but how is this different from a mirror image linear prediction in the regular nmrpipe application?
Yes, we consider this as an alternative to linear imaging, linear prediction. And I think it's more robust and it's easier to use.
I see.
And it can be done. Like I programmed such that you don't even need to generate a sampling schedule. Okay?
I see.
So I can detect that when there's no sampling schedule, you really have to set some XT, or default is 50% anyway. I know that you want to do linear prediction type of reconstruction, and it will do it that way.
So can this be used on a linear data set that is acquired linearly in T1?
If you need more resolution, I say yes. If you need a linear prediction, I say yes, do this way instead of linear prediction. But I tell you what, if some peak is not resolved in your spectrum, it's unlikely it's going to be resolved. So it's good for something that it's already resolved, but you want to make it narrow so that they resolve better.
Look better.
Not look better, also more resolved, right?
Okay.
Yeah, look better too, of course. That's important too. But
Frank shows this with IST also. He shows that you can improve the resolution.
Yes, certainly. Any NUS, yeah. So I think that people realize that nowadays it's better to use NUS to do linear prediction, okay?
Okay.
And I think Jeff did that first.
Yeah.
All right, okay. So another question, someone else was asking questions.
Yeah, I was asking the question following up from the first point scaling. So you just briefly mentioned about like the first point scaling, how it relates to the linear phase, right?
Yes. Yes.
So can you please repeat it, like, so I can take a note?
So I look at linear phase. If it's 0 or plus, from negative 45 to plus 45, I use 0.5. If it's a 180 plus minus 45, I use 1. And if it's 360 plus minus 45, I use 1. Any other value, I don't remember anymore. Yeah, I think the default is...
There's minus 90, 180 also. Phase correction where you have a half dwell delay introduced into the T1.
That will be 1, yes, because the linear phase is 180, yeah.
Yeah,
1.
yeah.
Okay.
So
yeah, it's important. Otherwise, you get a baseline problem.
Correct. The zero order and first order, 180 and minus 90, or some combination of that.
Yes.
Depending on
how
it's acquired.
It's completely depending on P1. Okay, that's why I save you with an additional parameter for the scaling factor. All right. Okay.
And that's important for the direct dimension as well.
For which
just
one?
For the indirect. That is important for
the
the direct.
Yes, yes. The direct dimension, it's saved in the header, so I know it. That's why I don't need to do it. Okay. Like here, the Y dimension, you don't need to do anything. I read from the header. Now, one thing is, since you mentioned that, I want to point out to you this. This SP function is really universal. You could get another GLB, negative something, or ELB, like say 6 Hertz for exponential line plotting on top of cosine, right? So this is a composite window function. So you could do that. But some people could also do something like this: NMR pipe -FM EM -LB 6 Hertz, and then something like this, right? Don't do that, because the second processing function will overwrite the first one, and the header SMILE will only see this line, the second function, instead of the first one. So SMILE will use the long window function for the direct dimension. So instead, I suggest you to use a composite window like this, okay? And then every parameter will be saved in the header, and SMILE will pick it up, okay? And in the end, you don't apply another equalization after this, unless you can remove it, reverse the process and apply a new window. That's okay. Okay.
Can I just confirm something?
Yes.
That you said? So someone asked about extending the direct dimension of your spectra.
Yeah, it doesn't work that way. I'm sorry. Direct dimension, we assume that a good spectroscopist should always optimize the direct dimension. And my practice is that you always acquire longer than you need. It doesn't hurt you anything, just will end up with a bigger data processing. Not big data, but big data set, okay? But you could always truncate it or use different equalization like exponential broadening if it's too long. But if you are quite too short, you cannot get data back after the experiment is done, okay? So always acquire something longer than you need, and then you work with it later. So I assume you don't need to extend the direct dimension. Okay.
So what do you mean by longer than you need is like for the direct dimension?
For example, for protonated, for bimolecular MR, we rarely do more than 100, 120 milliseconds, because the HNH alpha splitting will leads to splitting, okay? You get a poor, signal to noise and resolution anyway. So we usually do that. We could always run longer for 150 milliseconds. Your decoupling, of course, you have to be a little bit careful.
Yeah.
For that, right? So you could do that, or in some case for large proteins, 60 milliseconds is more than enough. You acquire, for example, 100 milliseconds of acquisition time. Okay. So in the talk, I suggest you use more spectral width, and when you do that, you also make sure that you need a larger TD value, so that the total acquisition time is what you want. Okay. So that's what I mean. You acquire more acquisition time so that all the signals decay to 0. And yes, you need a larger storage space, but at least you can get optimal resolution in the end for the direct dimension. So let's run this, okay? So that's how fast it is, and these tells you really what's the largest signal right now divided by the noise value and divided by the so-called multiplication factor, which is default is a 5. Okay, so when this reaches 1, everything is done. All right, and this something called a scaling factor here is really because you extend the signal by another factor of 2. So if you don't scale them, your peak height will be higher. And I try to use simulation to figure it out, saying that, hey, a downscaling of 0.8% will make your signal as high as what you have without extension. So this way, like I say, I try to make the real signal peak height in the data that you recorded, okay? Like make the peak height consistent with the data you recorded. Otherwise, you get artificially boost of the signal, and you might think, hey, my signal to noise is actually higher, and that's deceiving actually, okay? And by default, it's 0, meaning that SMILE will calculate automatically for you. All right, so we can use this script, the view spect, to look at the 3 spectrum at the same time. This is 28 millisecond. This is 28 millisecond with linear prediction, like of NUS processing. And this is really the experimental data of 66 millisecond. If you zoom down on this overlapping region, you see that resolution is higher than the original one, although it doesn't look like quite as close as this. Okay. In reality, it might be less than 56 millisecond here because you need a gradient time. I think it's about 23, 24, and this is about 54, 55. Okay.
Can I ask a question here?
Yeah.
Don't close the spectra. Don't
Okay.
close the spectrum.
Okay.
So in your carbon dimension, you should have a quartet, right, for the metals?
Should I what?
You should have a quartet, right? 1:3:3:1.
Yes, quartet, yes.
Yeah.
This is a quartet.
But it seems to me like the intensities of the multiplets are off. Is there some explanation for this, or?
No, the intensity is right. Look at this.
No, it should be 1:3:3:1, right?
Okay, no. If you run 1D, it's a 1:3:3:1. But if you run HSQC, you start from antiphase. It's 3:1 to 1:3. I'm sorry. Yeah. Okay.
That's correct. Jinpa, that's correct. This is Andy.
Yes, I know that's
and
correct.
I know Siddhartha who's asking the questions, but this is absolutely correct.
Yes.
I said, but no, this is correct.
Yes,
Okay.
It depends on your scope from U phase or antiphase, okay?
Okay.
Yeah.
Send me an email, Sid.
No, I'll work it out, Andy. If I'm in trouble, I'll call you.
Right. So
I never thought about it in the 2D.
It takes a long time, but I want to show you another way that Frank does in the directory called Frank. Unfortunately, I didn't update this because I copied the script to a low level of photo. So open up run draw.csh, and you need to edit this as upper directly for the test.fid. Okay, and then if you run that, actually this is the Frank stuff that allows you to graphically set up the processing script. Okay. And as I said, it's existing. You have to look at what Frank does, his seminar, his workshop, his YouTube video to learn this. I'm sorry. I did this at some point, but since I don't use it every day, I forgot how to use this. But it's existing. You can play with this, and in the end, Frank will generate a script like this. Okay. So basically, generally this script, and you can expand it, and it becomes something like this, all right? And it should be similar to what I was doing, but he's more setting more some of the parameters than I have. So if you don't have any other question, let me move on to second. Oh my God, it's 1:42 already. Okay, let's go to another one. This fixed data points. Okay, here the processing is really standard. Okay, it's really. Let me bring you to this. How do I? Okay, first of all, how do we look at what data point is bad and what is good? So here's the data set right here. Top spin. You don't have it. You probably don't start it. We don't have enough license here. If you go to FID, you see that this is a bad FID right here. And if you zoom them, okay, and then you can zoom further, you can put a cursor on it. You can read out somewhere here, what is the FID number of for the FID that your cursor is on. And you can read those and you can figure out what is the FID number that has bad corrupted data. So in that case, this is top spin 2. So I don't have the log. Instead, I generate something like this. You just give a range of the FID. I think if you have a single FID, you don't have a range. You don't need to have a range. The script will work. If top spin 3, you get something like overflow DRU, or no, log DRU1.text, and it will give you something like that. Okay, these are the FID number. And this one, of course, I artificially made just to show you. I copied it from a different data set and I made a FID list saying that you have 8 scan, and 1 means that the first scan of that FID is already, the number overflow is 1, like 8 scan, only 1 of the scan has overflow. And sometimes you get an 8, sometimes you get a 4, sometimes you get a 2. And so, so this one is from top spin 3, but if you don't have top spin 3, you need to manually figure it out and then come up with a text file like this. And then after that, you could just use my script included in this data set. You need to tell the program how many increments, both in Y and Z dimension, the 2 indirect dimension, and then you give the FID list, the one, if you're top spin 2, use a list you come up with. It's just a list of number or a range of number. Or if you do top spin 3, you can use this followed by top spin log file. Here, I set it to none. You don't even have to set anything. Default is none, okay? And then you can generate the sampling list, all right? The whole thing here is standard. And the not standard part is really just included this script and you generated a sampling schedule. Now, one thing I want to tell you is that for those bad, as you can see, this is a fully sampled data set. You don't need to subsample the good data points, discard the bad data points, and then re-expand it as you might need for the other program. Because what Smile does is I read the whole data set in and read the nuts list in, and then set those data points that not in the sampling list to 0 automatically for you. So you don't need to worry about the process of downsampling and expanding. Hopefully that make life a little easier, okay? And then after that, we have NMR, we have XYZ, I guess. This is just the normal processing, okay, 3D processing, and without Smile. And then I have this thing with Smile, okay? It's very similar, just adding this part, and then commented out the episodization function, okay? A few things that I want to point out. One is that we set xt2, xt, and yt to the increments in here in the fid.com because we don't want to do extension in this case. The user decides that the resolution is enough, so I don't do that. And otherwise, if you don't specify those two, it will do 50% extension by default, okay? So this will be 80, 90, this will be 225, okay? Another thing is that you have to set the phase, and this phase is obtained by phasing the regularly processed data. Another thing is this. you see, for Bruker, standard Bruker data point processing, the states TPPI, you always need to call it alternation, because every other data points, you need to negate it, okay? So that you get a correct spectrum. If you have alt for your FT, if you need that to get a correct spectrum, you need all X alt or Y alt was kept A for that dimension. Now, if it's just zero phasing, you don't need it, but I suggest you it's good practice to keep it consistent with your regular FT processing, okay? And sometimes you have a negate, you also do X nag and Y nag, okay? These are the things that I say by default, you may not get optimal data, but you need some manual, setting to get optimal processing, okay? So I guess we don't need to process this. Let me just open the data for you, view spec. And you see, this is the one without fixing. And this is the one with the bad FID points fixed, okay? And what time is it now? 50. Let's go to next example for HNCACB.
Jim, I have just a question for you. Is it possible?
Yes.
This is Massimo. Just let me know if you test this script also for topspin 4 or the NEO spectrometer, which are in the market now.
You mean here?
Yeah, the NEO, this is, okay, topspin 4, perfect. Because I just understand that this is tested on topspin 3.
Tested, what do you mean tested?
Tested, I mean the overflow handling.
The what handling? Sorry, I'm sorry.
The overflow. I mean, when we have
overflow. Yeah. So I loaded data here, but it was collected on topspin 2.1. The data was recorded on a machine running topspin 2.1.
Okay. It's not native. Okay.
Yeah. Sorry, no. Okay. So HNCACB.
Can I ask a question about bad point correcting?
Yeah.
So I was looking through my directories for my personal data, and I can't find it. If there are no bad data points, are the log files still generated?
Yes, topspin 3.1 always has the overflow log file. And I tell you what, sometimes it's a false alarm. A lot of time it's really when your receiver turned on too quickly after the pulse, it still has some of the junk in the probe that it can pick it up, and it's a particular happen for cryoprobe. And in that case, you can set the DE time, data time, delayed DE, okay, to be a little longer. The default is 6.5 microsecond. You could set it to 30, 40, and of course that will screw up your linear phase, but you could actually compensate that in the pulse sequence. If you have an echo right before detection, you can always account for that delay. So I'll say whether it's legitimate or not, you look at that FID, extract that, do Fourier transform, ask yourself, does the spectrum look like corrupted? If it's not, ignore that. If it is, yes, use those data, and you should have it.
Hey, Jinfa.
Yes.
Okay. So yeah, for most of the bioNMR sequence, if you end up with an echo, anyway, the dead time DE shouldn't matter, is it not?
That's true. That should be very true. But for some reason, the delay, the dead time, it still matters. Okay. Yeah. For some reason, I don't understand it. You are right. If we have an echo, we have a few milliseconds.
They shouldn't care. Yeah, really.
Yeah,
between 6 to 20.
For cryoprobe, for some reason, at the moment when the receiver turn it on, something happens.
Yeah, I mean, the cryoprobe, I think that also is a cold preamp. Probably that has something to do with it.
Yeah, so you are right, yes. But more often happens when you have single pulse without an echo and followed by detection immediately.
Yeah, then it's a problem.
Very critical, yes. You are correct, thank you, yes.
No problem.
Okay,
Jinfa, I'm sorry if I could just interrupt for 1 second.
Yes.
It's come to our attention that unfortunately the data copying may have failed for all of our attendees today. I think this comes
really?
apart because we're doing a multi-part workshop series, and that's changed how our data copying normally functions.
Okay.
My apologies for that. What we're going to do is copy data to everyone's home directories beginning soon, and you'll have that available for this afternoon to follow along with the tutorials.
Okay, so I will try to slow down, and so that you can just look at this and interrupt me whenever you need to. And we're gonna hit the 2:15 or 2 o'clock quickly, but I'm dedicating the whole day. So if you want to stay, you can stay. If you don't, feel free to leave anytime. And after you get the data, I suggest you play with them. If you have any problem or question, let me know. All the scripts are there, okay? So let's move on to HNCACB. And it's a conventional HNCACB, and I'll show you how I actually post-program that. So this, oh geez. So this is how I programmed it. It's not even RQD, RPD, not single partial component. So you need to have a lot of loop. So first T2 loop, then you have a, yes, that's a T2 phase loop, and then T1 phase loop, and then you end up with an increment, okay? 3 loops. And you can look at this later if you're interested. But when you do RPD, this is simple. So I no longer do this kind of programming anymore. You only need a 1 loop for this. Okay, so first thing you do is really type Bruker, and you do this, read the parameter, okay? One thing is that, let me see if this is the case. Oh, this is a full data set that the whole thing is completed, okay? So that's good. If the experiment is not completed, usually in the ACQ2S file, you actually see a number, okay, some strange number. And usually it's smaller than the number that you set it to, okay? So anyway, where's my window? Somewhere here. Yeah, so, okay, if the experiment was stopped before the data completes, this number, it's NUS samples, like the amount of data points that has been collected, okay? It has to be smaller than this. For example, if you stop halfway, let's say just add it to 8,000, okay? You enter, and these entries becomes highlighted because it means that you have to click read the parameter again to update those two. The reason for that is that, let's say if you only have something, remember this, okay, 212 and 300 data points, 300 and 212 here. If you, let's say, only have 100 data points, for example, and you read it again, you see that this has only become 297. This has become 209, right? Because when you stop the experiment earlier, you may not have hit the largest increment number contained in the sampling schedule. And therefore, the valid data points for the time domain, the total increments for both dimensions need to be updated. Okay? So for real experiments, if you stop early, if you don't stop early, that's fine. If you stop early, read the parameter and calculate from that TD value from ACQ2S file. And then that number should be divided by 2 for NUS for 3D and divide by 8 for 4D. And then you set that number to this value, that corresponding to the total number of data points in the sampling schedule that has been recorded. And then you hit read the parameter again. Those 2 values will be guaranteed to be okay. Otherwise, the conversion script will complain because you don't have enough data, okay? Because you only expanded to the largest number. Yes?
Sorry, can you check this using the user interface in Topspin?
Yes, certainly. Okay, yes. So what you do is this. You go the whole spectrum and you put a cursor at the end of it and you figure out what's the number of total number of FIDs collected. But you see, when you have a lot of them, it's not easy to do. You have to zoom them, okay? And then you have to make sure it goes to end. How do I do this?
Hey, Jinfa.
And
there is a...
Hey, Jinfa?
Yes.
Even in EDA, I think in that status parameter, like if you say DPA, I think it shows for
yes,
the total.
In the EDA, and if you go to status parameter,
yeah, it will show you.
Same
click
will show
that.
up. Yeah, that's true too. Yeah.
Yeah.
I'm usually just working with the ACQS file.
Yeah.
And you can just grab that from that number, okay?
Sure.
But I think Frank nowadays actually could. Let me see. Let me do test like this. I think Frank talked to me about this, and we were able to actually doing this. For example, let me edit this number, okay? Instead, I'll just say, put this as 1, okay? So it's a lot less data, okay? And then if you do Bruker.nus, and if you read, you will read the correct, oh, it doesn't. I thought Frank does that, but it's not, I'm sorry, okay? Yeah. Yeah, it's not. So I'll talk to him. At some point, he made it so that this thing actually read it from the SQL2S file and then calculate, collect the NUS samples. Okay. Anyway, it's not. So, and if we save, if we set up those things, because these are not set up because it's my own sequence, and you always need to play with it. It's not always recognized. Okay, if you use a Bruker one, Frank takes good care of it, so it should be all correct. But still, I suggest you to manually, because you know what is the F2 dimension, what's the spectral width, what's the carrier frequency, and things like that. So I've already saved this something as called fid.slow. So what this does is that first expand the SO file, okay, to SO4, so it's still Bruker data format. And then you read that in and treat this as a fully sampled data set, and then you convert them, okay? I call it slow because you see, you have to convert every data points, even if they are 0. They are just added in by nus expand.tcl. And for this 3D, it might be okay. But for 4D, it could be very slow you down a lot for this conversion process. Okay, so there's another non-conventional way of doing this, and let me show you how. So this is the way, fid.com. That's the fast way of it. So what it does is that instead of expanding the data first, I'll say, I'm gonna convert the data first, whatever collect the data. For 1D, for 4D, this might be just 1% of the data. So you only deal with 1% of whatever. Okay, so that's why it's faster for 4D, and for 3D, in some cases, a large data set like this is a large data set. It's also faster. So the difference is this: you really have to set every other dimension to be real. Okay, only the first indirect dimension you set it up as either echo and echo or not. And the YTZT, the increment number should be correct, but the total number of data points for YN should be the total number of FIDs, which is what you read from ACQU2S file. All right, and that's just the real, and set number of dim always to 2. Okay, this NUS dimension 3 is not critical. It's for, I don't know what it is for. You don't need to, but you could just set it. Oh, this means that the whole data set is 3-dimensional, but you don't need that information. This program will figure it out as 3D, okay? So after this, basically we treat the whole thing as a 2D regardless of dimensionality in the input data. We always treat it as 2D and just convert it, okay? And then you can follow it up by regular conventional processing of that direct dimension by first, doing time. In the time dimension, you remove the 0 frequency for water. And then in this case, I collected too many data points, so I cut it down and also apply the window and then regular processing, right? And I use a flat to do baseline correction in the direct dimension. And then I extract it, and then I write it out. Not write it out. Then I do expansion. Run NUS expand inline like this, okay, in the pipeline, and then expand the converted data, already processed the data to become, something in the end, which is direct dimension processed, NUS expanded, okay? So you see, this way, you don't have to process all the zeros. Those zeros that you inserted by NUS expand is still zeros. That's why it's faster and it's preferred way, but unfortunately, it's not a standard way in NMR pipe. But with a few tweaks, you can always set this up and have a fast conversion. I'll show you how fast this is. Oops, not so fast. Why there's nothing? Oh, I think I set all the verb to 0, so there's no information out of here. Okay, but if you run the other one, I'll tell you it will be a lot slower than this. Okay, so it's done. Oh, yeah. So the conversion even takes a little while, and now it's doing expansion. Okay, so let's leave it. Let me go back to HNCA here, another window. So let's look at the SMILE script. So again, since the direct dimension is already transformed, so you can read the data in. Or the other thing that I want to point it out is that you see that the output is saved to Z dimension, okay? Because the direct dimension should be always the last dimension. Is that done yet? Still running it. Okay. SMILE is that, so you read that in and you set a SMILE up, and you can just use this starting from the conventional data and add the SMILE line saying and comment it out, the episodization window, okay? And here I use ZF, 0 filling 1 for faster processing. So here, let me explain the parameters here. It's HNCACB, the nitrogen dimension, which is the X dimension. It was collected, like I explained it, using the mixed time. So first the 31 increments is recorded as a constant time, then followed by real increment, okay? So in that case, you set this to 31, and then the resolution is already very high, and we don't need to extend that. So we set XT to 300. Y is a constant time completely, so we set YCD to 212. We don't want to extend the indirect dimension. So YT should be also set to 212, okay? And there's a Y nag needed for the CACB dimension. That's why there's a nag here. I use Y nag, all right? You might wonder how I figured this out. Let me tell you. If you open up the pulse sequence, if you go here, you see that this mixed time is done by if condition, right? If D0 is larger, you could do increment, you could do decrement for D0. Okay, that's the constant time part. Otherwise, D0 stays, but you actually increment D10 and D9. Okay, so in this case, it's really D0. The question is really how many D0 you can decrement. And therefore, you can go to ACQUS file and find it out what is the D0 here. It's 11.65. Remember that number? Then you look at IN0. it's 375 millisecond, right? So what you do here, oh, oops, I want to, sorry, I need another window. Python. So 11.65 divided by 0.375 or something like that. Yes, it's 71. And that's the constant time part. That's how you figured it out. Okay? And of course, I mean, this mix the time thing, probably not so many people use it. I see a lot of questions in the chat. I prefer people just turn microphone on and just ask me.
Sorry, just a question about extending the size of a fid in Smile.
Yeah.
So it applies by default 2 times 0 filling.
Not 2 times, no, sorry, 1.5. It's different from 0 filling, really.
Oh,
and Frank call this NUS ZF. It's NUS 0 filling. It's really not 0 filling.
Oh, I see.
Yeah.
So we don't have to worry about that when determining the new maximum fid size?
Right.
Okay.
Yeah.
Thank you.
It really depends on whether you, I mean, the reason we do this by default is that we assume that a lot of NUS is resolution limited. And even with US, you might not want to sample out too long for saving signal to noise. And therefore, something like up to 1 T2. And if you collect it to 1 T2 by extending this, you could still get a little bit higher resolution from it. Okay? It's debatable, but that's how it was programmed. I guess anyone has any question about the Smile setting over here? If not, I'm not going to run it because, as you can see, it takes a while, even for this data set, even for converting. If I move the scratch disk, it might be faster, which I should have. And there's also baseline correction after this, okay? After the everything's processed, and you do ZTT to put the proton dimension back to the current dimension, then you write it out. So I'm gonna just show you the data, okay? And you see that this is HNCACV, so CACV has a different sign. That's why in the projection you got a positive, negative, and it's a mixture of 150 micromolar protonated and deuterated sample. That's why you see if you go here, you see that those two peaks, they're very close to each other. And that's because one is deuterated, one's protonated. And from there, we can measure chemical shift of carbon, C alpha, C beta, when it's protonated and when it's deuterated. And for example, if you run this, if you put a cursor here, type L, you'll move to this plane, okay, right here. And if you put a cursor on this peak, on this slice, it moves a little bit. You see that? So if you get this, and if you get the vertical line, you see that the difference, the chemical shift, the difference in the C alpha for the C alpha, and over here as well, preceding and intro residual. And anyways, this is how we measure the deuterium isotope effect. And the work should be published already. I don't know which year. I think it's on JBNMR or biochemistry or something like that. All right. Next example, it's already 2:12. Should we take a poll whether we move on or not? Adam?
Yeah, sure. I can send a poll to everyone here. Let's see.
This is. When you guys are respond, I'll probably just keep going for another example. let's see, what's the next example I like to share? Oh yeah, this is nosy RQD stuff, okay? I put in my pulse sequence over here so you can look how easy it is to program this.
All right, Jinfa, well, we're at a 50-50 split. So it may be best to offer this as kind of as an optional extra segment. If some people are late in the day and need to get going, we could let them go. And if you'd like to continue with another example, that'd be fine.
Okay. Okay. Yeah. I mean, people, whoever want to leave, they can just leave, right?
Yeah.
Yeah. So, okay. I'm going to.
Well, then for those of you that might be signing off, thank you very much for joining us. It's great to have you part of these workshops. There will be a follow-up email with some extra announcements and more info, and a survey will be coming your way. So please help us out by filling that out. Thanks a lot.
Yeah.
Thanks, Adam and Jinfa. It was wonderful, wonderful session. I really enjoyed. I had to go, but thank you, Rajan.
Okay. Well, thank you. If you have any more questions, you can always email me. Okay.
Yeah, that's what I was thinking. Yeah. Thank you.
Okay.
Bye.
So over here, it's the nosy HSQC, and it's Bruker doesn't do that for random quadrature. So I first define 4 sampling lists like this. Okay, 2 are for the increments, 2 are for the phase 0 or 1, and you need to define a few delays and also initialize some of the values like this. And then before the post program starts, you have to read those values from the list and then calculate the increment and decrement value. And then you do also calculate the phase increment and you set them. And that's it, really, the regular pulse sequence. And in the end, you do the same thing like you did it before, again, and followed by a loop like this. So it's a single loop for multi-dimensional, any dimensional, okay? Because the number of dimensions is really handled by the sampling schedule. The conversion is quite standard. In this case, I have this RQD expand.tcl, which is actually extended from Frank's NUS expand.tcl, and almost using the same, parameters, okay? And I set to YTZT is because remember that I was demonstrating that if you hit the sample earlier, then you might not have hitting 85 and 180, right? So that's why you need to figure out what's the maximum value. So another way of doing this is that you just set YTZT to this. You always expand the data to 85 points and 185 for the 2 indirect dimension, okay? So this is the tool. It's available if you have a latest SMILE, and everything else is the same as a conventional NUS. Now in this case, I expanded first, but followed by conversion. I think at that time, my thing only works with Bruker data, but now it works with pipe data as well. So you could do it in the way that I explained, convert and then followed by expansion. And even if it's real NUS, it's always a good idea to run a conventional processing like this without a SMILE, okay? And look at the spectrum, ask yourself whether phasing is fine, negation, negate and alternation, sign alternation, everything is fine. And then you will adding SMILE into that conventional experiment like this, okay? And again, everything else you have been familiar by this point. The only thing that I want to say is that this XEA, meaning that the X dimension was collected with echo anti-echo, so that Bruker knows what to do. Not Bruker, SMILE knows what to do. Like I explained in the talk, you take the cosine and sine component, and then you combine them and form this echo anti-echo type of data. Okay, so I'm not going to run it. I'll just show you what the spectrum look like. And if you go to some of the plane and you see data like that, I use the counter level of 3, multiplication of 3 just to draw this faster. Okay. All right, that's another example. Also, right, I want to talk about this. There's a tool called RQD sample. So this will allows you to sample the full quadrature or partial quadrature. Even allows you to order the sampling schedule, okay? And I suggest that you can just type RQD sample.py help. You gather the help file for what you need to do. You just need to tell the number of data points in our indirect dimension, percentage of sampling, 0.1 for 10%. Alternatively, you can just tell what is the number of sample. And if you specify both, I think the script takes the largest one, whatever larger, more sampling, I think, I forgot, okay? Allows you to specify the sampling random seeds, and also allows you to say, you can, for example, you can do this, you know, Y dimension in full quadrature, both components, but Z dimension in partial components. Because if you have echo anti-echo, you don't want to do full quadrature, partial quadrature, then you do full quadrature. So you can do mixed. And this allows you to get a, you know, just to evolve one indirect dimension so that you can test the plane without running the 3D. Single column is really ought to put the whole the list as a single column, because TopSpin 3 does not read multi-column lists. And here you can sort the sampling schedule. You can order that. Okay. Anyway, so I guess I don't know if we have. I mean, this is an RT experiment that I showed you guys. Talked about it previously. Everything is standard except that we need a form. I mean, it's interleaved, right? The reference and attenuated are interleaved. So we have to process them so that you generate two FID right here, the two FIDs. And if you look at using show header, oh. You see that it's actually pseudo 4D, okay? Only consisting of 2 cubes. And this is done in the script by everything after the conversion, everything after this point, all right? You can go home and take a look at that. And then there's also, I provided this thing called a series.com. So what it does, I take 2 3D and form the pseudo 4D. And in my pipe has this series.com. Yeah, so that's for forming 2D. From 2D, you form pseudo 3D. So I extend that to series 3D. And that's provided too. And the SMILE reconstruction is pretty much conventional, except you do something called pseudo ND. Okay, you need to tell SMILE this is pseudo ND. And then SMILE will figure out how many cubes you have, and it will try to reconstruct the weaker planes or cubes from the first strong reference plane. So, but intensity-wise still follows whatever in the plane, and only the peak position and line widths are derived from the first plane that has better signal to noise, has more accuracy about peak position and line width. Okay. Another thing is that before SMILE, for something like this data set, I had to do something like this for poly. Basically, I want to define the node list so that this program knows better what is baseline, what is not. And in this case, you don't use auto. This auto means that automatically determine the baseline. So you can go home and try something like this. So everything else is really standard over here, okay? The spectrum, it's like this, you see? So if you go to somewhere, you see peaks like that, and this is the first cube. If you go to A equals 2, the second cube, you see it's some negative and some are just disappear. That's because the coupling is there. and the signal is attenuated, and you take the ratio of the two spectrum, you get a coupling. Okay, this everything is all pretty much covered. This iPad and this 4D, I'm not going to talk. It's really just providing you as an example for running 4D. Okay. Also, the FID conversion script for 4D, I always do conversion first, followed by expansion. It will save you a tremendous amount of time. Just allow me a few minutes to briefly talk to you about this IPAP C13 decoupled C13 detection experiment. Okay, if you come over here to the, let's see, where's my, oh, here, my top spin, and if you open up and if you type EDA, see, there's something called AQ sequence in Broker. And here's 3, 2, 1. But if you look at the pulse sequence, Broker use 3, 1, 2. So when you run this experiment, use 3, 1, 2, use a fully sampled, it follows this AQ sequence in the pulse sequence, 3, 1, 2, meaning, how do I close this? Meaning that this is direct dimension. F1 is the T2, is the first indirect dimension, and F2 is the last indirect dimension. So that's okay. It will interleave. Make sure the interleave loop is the innermost loop. However, the same user just change this FN type to non-uniform sampling, okay, from traditional to non-uniform sampling. Broker ignore its own AQ sequence, instead using the standard 3, 2, 1, okay? And the problem of that is that the interleave is wrong because it's no longer innermost loop. Instead, Broker acquire the direct dimension and the first indirect dimension, T2, and F2 in this case, and then interleave that, and then come with the indirect dimension. So in the end, I could not separate the in-phase from anti-phase spectrum, the two interleave the spectrum very easily. And even if you use Broker's own IPAP split or split IPAP or whatever script that they provided within TopSpin, it did not work. It took me a little while, and in the end I figured out that you just have to use something called a Q-mix here to separate the quadrature component like this. For example, here, this means that it's a 4-channel, okay? You take 4 FID and you reduce the 2 FID. So in this case, it means that horizontally is the number of FID, okay? First row is the first FID, third row is third FID. So you sum the first FID and the third FID, and the column standing for the output, it's the first FID. So the first FID in the output is equal to sum of the first and third FID. And the second FID in the output is the difference of the second FID and the fourth FID, okay? And that gives you one of the components. And if you do another one, take the difference in the first column and basically sum in the second column, you get another component. And the downfield, upfield components already co-added for IPAD. And then here I shift the one component, here. I phase shift the one component relative to the other by the amount of splitting, which is 53 Hertz for C prime, C alpha. And then I use the add NMR to add them together, it becomes a one data set. And then I do expansion and followed by reconstruction. The reconstruction is normal, it's just conventional. And this way, we instead of reconstruct 2 data sets, we reconstruct 1 data set with better signal to noise, okay? And the reconstruction should be really the conventional, and everything should be already covered in this talk. And if you look at that, you see that it's not a nice data set, but it's there, okay? peak is detected and it's in the right position. I think the user was just testing and got trouble, couldn't process that whenever he runs as NUS, why the whole thing works when it's fully sampled. That's really it for the demo.